It's just that everything else I'm worse. So that made it very easy. I know some people are, when they had to choose a major, it's difficult. Like some people have to do some, exploration for a few years before they find out what they want to do. For me, it was easy. Yeah. It was either astronomy or computer science, and my dad said, computer science. I'm asking that question because in 2 weeks or so, I'll be going to Career GPS. Has anyone heard of Career GPS? Okay, it's an event for high school students, mostly targeting either late middle school or or high school students, and basically just to expose students to different types of careers or opportunities in a college or university, so they can choose what to do after high school. And one of the things that I'm supposed to do is to figure out what to tell the students about computer science. So that's why I wanted to ask you that question. Yeah, computer science is one of those things where for anyone who's not really interested in the subject matter but only interested in the money, I think it's going to be quite painful to get a job as a computer scientist without the interest. The money is not really the best. I mean, there are better occupations out there. For instance, being a lawyer, and I'm not just saying any lawyer. If you combine a JD and a computer science degree, that makes an awesome combination because you can work with patents, patent applications and stuff like that, and there's a lot of money in patent applications. So, all right. So that's just a general question that I wanted to ask. I made a new page here. It's called Logical versus Bitwise Operator. So I want to get this done first, so that you guys can do the homework exercise, which is base conversion and bitwise operator exercise, and then we're going to go back to the other topics. In case you guys want to kind of read everything in the right order, I can just go ahead and reorder that. So this way, it looks correct, like it's in the right order. So we'll go ahead and move this. Did I move it? Yep, but not all the way here. Okay, so now that the order is moved, things are kind of right in the right order. All right, so we'll start with this one here, which is something that it's a little bit new. It's not going to be too difficult. How many people have some exposure to base conversion prior to this class? Okay, base conversion, like from base 10 to base 2-ish. Okay. Let me pose the question in a different way. If I specify a certain amount, okay, let's say $267.25. Is everyone in this class comfortable with coming up with the least number of dollar bills and coins to make up to the amount of $267.25? So instead of giving someone 26,725 pennies, you would have given that person are there $200 bills? They're out there, but not common, right? So you can give the other person like two $100 bills, one $50 bill, one $10 bill, one $5 bill, two $2 bill, two $1 bills, and a quarter, right? All right. Well, if you can do that, you know base conversion already. It's harder. Base conversion is easier than what I just said. Coming up with the right number of bills and coins is actually harder. Okay, so we'll start with that and basically move on and talk about something else. The first thing here is kind of important because what is the difference between logical and bitwise operators? A logical operator means it works on true, false values. Okay, the entire variable or the entire expression is either true or not true. In C and C++, there's no such thing as true or false. There's only zeros and non-zeros. A zero is the same as false. A non-zero is the same as not false, which is true. Okay, so we'll go back and explore that part a little bit. A bitwise operator, on the other hand, means the operator applies to individual bits of a particular number. Okay, so we have to kind of understand how numbers are actually represented inside the computer before we can talk about that. And that's why we start with this topic here. What exactly is a bit? A bit, B-I-T, is an abbreviation of binary digit. The B comes from binary, and then the IT comes from digit, the last two letters of digit. And that's what we call a bit, B-I-T. Okay? Now, what we use, on a daily basis are decimal numbers, okay, base 10 numbers. And that is really not exactly a good base to use. We use base 10 only because we have 10 fingers. Okay, that's the only reason. Okay, it's not a very useful base otherwise, other than the fact that we have 10 fingers and it is just, easy to start with. And then we are moving on to this value here, 267 and 0.25, okay, and a quarter. So one way to rewrite this number is to spell it out. Okay, it becomes 200 plus 60 plus 7 plus 0.2 plus 0.05. Wow, that's hardly college, material, isn't it? I mean, come on. I mean, elementary school students can break up a number and spell it out in individual units. So what we'll do is we'll make it more college appropriate by breaking down this number into this form here. Okay, so now we have 267.25 being 2 times 10 to the power of 2, which is 100, plus 6 times 10 to the power of 1, and 10 to the power of 1 is just 10. Okay, plus 7 times 10 to the power of 0. 10, any number to the power of 0 is 1. That's right. And then plus 2 times 10 to the power of negative 1, which is 0.1. Plus 5 times 10 to the power of negative 2, which is 0.05. Okay, no big deal here, right? I'm just rewriting 200 to a quantity times a power of 10. I'm rewriting 60 into a quantity times a power of 10, and so on. Is there anything new here? Nope, nothing new under the sun, right? One thing we also want to notice is the number or the quantity of each power of 10 can only go from 0 to 9. For base 10 numbers, that's the limit. Okay, for each digit in a base 10 number, each digit can only go from 0 to 9, making up 10 choices per digit. Are there any questions about that part of decimal numbers? All right, very good. I think we have a good understanding of base 10 numbers. Is that okay? Okay. Well, base 2 can only be easier. Okay, so what we'll do is we'll take a look at base 2 first. So when we look at the base 2 number in this class, I will start with a value, and if you see a suffix of 2, it means it is explicitly a binary number. Okay, because if I just give you 101, okay, 101, is it a base 10 number, meaning it is 101, or is it a base 2 number, which means 5 in base 10? Well, we don't know. If I just say 101, it can be base 10, can be base 2, can be base 3, can be base 4, can be any base. So what I usually do is if I want to emphasize a number is base 2, I either write it in text and say this is a binary number, or I use a suffix of 2 to mean that it is a base 2 number. In the case I cannot use a suffix, like using a text editor, there's no suffixing, I would use parentheses with a 2 inside after the number itself. So if you see 101 open paren 2 close paren, it also means it is a base 2 number 101. Okay. What do you think 0 represents in base 2? The quantity 0, right? What about 1 in base 2? What quantity do you think 1 represents in base 2? 1, right? 0 and 1 represents 0 and 1 no matter which base we're dealing with. Okay, that's relatively easy. So we'll look at the number the first number that is confusing, which is 10 in base 2. 10 in base 2 is not 10. Okay, that's how 10 in base 10 is the quantity of 10. But 10 in base 2 is the quantity 2, but represented as a binary number. Okay? Are there any questions about this part? No questions? Okay. So how come? How come this number is representing the quantity of 2 when it does not look like 2 at all? Well, the way it works is like this. When you look at a binary number like 10 in base 2, you can basically break it down into 2 parts. In other words, you look at this 0 here, and it's really telling you how many ones we have in this number. Okay? But since it's a binary number, you can either have 0 ones or you can have 1 1. Those are your only choices for the least significant digit in this case. When you look at the other digit, which is the 1 over here, it is telling you how many 2 to the power of 1s we have in this number. 2 to the power of 1 is just 2 itself. So this digit, the digit that I have highlighted here, is really just representing the quantity of the value 2 in this number. Am I still doing okay so far? Can you draw the a parallel between how a binary number is represented as opposed to how a base 10 number is represented? Let me just kind of scroll up back to the base 10 number. In this case, we have a 2 here, and a 2 is representing how many 10 to the power of 2's we have. Down here, this 1 is representing how many 2 to the power of 1 we have here. In other words, the place of the digit tells you, which power of the base we're dealing with. And then the quantity is represented by the digit itself. Is that doing okay so far? Sort of? Okay, there's another analogy that I can use later. Okay, so we'll take a look at a slightly more longer bit pattern here, but not necessarily more complicated. Yep, go ahead.
So that same, if that was 10 base 3, you would have wrote something like 1 times 3 base 10 plus.
Hello?
Yeah.
Okay, it's not 10, it is 10. Okay, because when you say 10, you are meaning the quantity of 10. This is 10. Okay, when you say 10, it is just a representation of a value. But the value represented by 10 depends on which base are we talking about. 10 in base 3 specifies the quantity of 3. Because because the 1 specifies how many 3 to the power of 1 we have in that representation, and there's 1, so it's just 3. Okay, let's break down a number. Okay, I'm going to use the whiteboard because it's basically stuff that I have already written. It's just that I'm making it a little bit more general. Okay, so let's pick A, B, C. So A is a digit, B is a digit, 3 is a digit. Okay, I don't know exactly the value of the digit. I'm just using a variable to represent the digit here. And we'll just make the base x here. So I'm not even telling what base I'm using here. I'm basically just saying that using base x, we have 3 digits. C is the least significant digit, and then we have B, and then A is the most significant digit here. What is the value represented by this number? The value represented by this number is A times x to the power of 2. Because the digit that is represented by A is 2 places from the decimal point here. Okay, so it's representing x squares. How many x squares do we have? And x is the base that we are dealing with here. How many x do we have? That's represented by digit B. How many ones? That's represented by the digit C. So ax squared plus bx plus c is the value represented by the number abc in base x. I know this is even more abstract than what we have talked about so far, but let's plug this into actual numbers. Okay? Let's say 106. Okay, it's a base 10 number. So you just plug in, 1 goes to a. So we have 1 times 10, because x is 10, x is the base, plus 0 times 10 to the power of 1, because that's where the 0 is, plus 6 times 10 to the power of 0. That's the value represented by 106 in base 10, which we also call 106. If I switch it to binary numbers, does it really matter? 110 in base 2. We have 1 times 2, this time because it's the base, we're dealing with base 2, to the power of 2. This 2 is there because this 1 is 2 places from the decimal point, or the implicit decimal point. Plus 1 times 2 to the power of 1, which is this one here, plus 0 times 2 to the power of 0, which is this 0 here. This is the value represented by this particular number. See, a number is nothing more than a particular representation of a value. The same value can be represented by an infinite number of numbers, because you can have an infinite number of bases. It's just that some bases are hardly used because it doesn't make any sense to us. Yep.
Okay, so if you look at the a plus s squared, so s right now has a base of abc, is it right?
Say again?
X right now has a base of abc, isn't it?
No. X itself is the base. So with decimal numbers, x is 10 because we're dealing with base 10 numbers. With binary numbers, x is 2 because it's base 2.
Okay, so how come on the one you have right here, 1 times 2 base 10 down below, but doesn't make sense?
It's because 2 does not exist in base 2, so that's why I have to re-emphasize this is actually a base 10 number. Well, it has to be at least base 10 in order for 2 to exist. Because 2 as a digit does not exist in a binary number. It's just like 10, the value 10 itself, cannot be represented by a single digit in base 10. So the value of 2 cannot be represented by a single digit in base 2 either. Yep.
So in 110, if there was another digit there, you would put 1 times whatever digit to the third power?
If I have one more, yeah. Yep, exactly.
So the farther away it is.
It's just like, in this number here, if I give you another digit here, c, then the value becomes, c times x to the power of 3 plus the rest.
Yeah,
Say again? Is that okay so far or not? I think you guys might be. Yeah, go ahead.
So a program would read all numbers as the value of base 2 instead of value base 10?
Okay, a value is independent to the base. You only have to specify a base when you are representing a value as a number. In other words, you are you regardless of your name, regardless of your student ID, regardless of how other people identify you, right? So your name is basically a number, okay? It represents you. Your nickname is another name, another way to identify you. Your student ID, your social security number, those are all different ways to identify you, but you are still you, whether you're identified by either one of these methods. Is that making any sense? So base 2 is basically just one way to spell out the value. Base 10 is another way to spell out the same value, and so on. Okay? Am I still doing okay so far? Another way to look at this is when you're dealing with base 2 numbers, just imagine this in your mind. Okay? In your mind, imagine that you can only have dollar bills of the following denominations: 1, 2, 4, 8, 16, 32, 64, and so on. In other words, the value of the bills can only be a power of 2. And so are the coins. You can have a $50, a $quarter, an $8, $16, and so on. That's base 2. Okay, let's take a look at whether that makes sense or not. Instead of using the whiteboard, I'm going to use a text editor here to do some base conversion. And it's under accessories, mousepad. Here we go. Okay, so let's take a look at this value here. Okay. So I have an amount. Okay, so I think people pay more attention when it's about money. So I'm going to specify an amount in money instead of just a random number. Okay, and this is base 10, by the way. This is a base 10 number which I use, paren 10 as an indication that this is a base 10 number. So there's no confusion of which base I'm using here. Okay, this is the amount that I want to specify, but you're using a base 2 system here. Okay, so that means you can have $1 bills, $2 bills, $4 bills, $8 bills, 8, 16, 32, 64, 128, and so on. Those are all powers of 2. In terms of coins, you can have a $50 coin, you can have a $quarter coin, you can have an $8 coin, and so on. So the question is, how do I come up with this amount only using those bills and coins? And I can only have 0 or 1 of one particular value. So you cannot just say, oh, we'll just have a whole bunch of $16th coins, and eventually we'll make up this amount. Okay, I want to use the least amount of coins and bills to make up this amount. So what do you think this becomes?
64.
Why did you pick 64 first?
Well,
Probably says that's base 2.
this is the allowed number.
Right.
And it fits under the 67.
Exactly. So we are picking the largest power of 2 that is less than or equal to the value that we're converting. Makes perfect sense. It's the same way that you do you deal with our current monetary system, our current denominations, right? Except you can have multiple hundreds or multiple tens and so on. In binary, it's easier. You can have 0 or 1. Okay, so there's no division involved. It's just comparing. All right. So if I do it step by step, we take care of the 64 first. That means we still have $3 and $0.375 left. How do I deal with the other one? Of the $3 and $3.375, I can only have bills of 1, 2, 4, 8, and so on. We pick a $2, right? Because 2 is less than or equal to 3 point something. It's the largest power of 2 that is less than or equal to this. Okay, so we pick a 2, then we have 1.375 left. What did we do with that portion?
128.
We take care of the 1 first, right? Okay, so we'll take up the 1, and then we have 0.375 left. So what do we do with that portion? Remember, the coins work, also in the same way. They are powers of 2, except they are negative powers of 2. So 2 to the power of -1 is 1/2. 2 to the power of -2 is a quarter. 2 to the power of -3 is an eighth. So can you guys do a quick conversion here and find out which coin is going to be less than or equal to 0.375?
A quarter.
A quarter. Okay, very good. So we'll deal with a quarter first, which is 0.25, and then we have 0.125 left, and 0.125, by the way, is 1/8. So we are all done. So the entire number is now expressed as quantities of some power of 2. Are we doing okay so far? Is everybody noticing that I have broken up this number into components, and each component is a power of 2? 64 is a power of 2. Yep, go ahead.
When you're writing it to the computer, does it matter if you put a 0 in front of the point?
I'm just lazy.
Okay, but it wouldn't affect anything?
The 0 is implicit, so if you just say 0.5, it's the same thing as 0.5. Okay. All right. So let's go ahead and rewrite this as powers of 2. 64 is 2 to the power of what? 6. Very good. And 2 is 2 to the power of what? 1. And then 1 is 2 to the power of what? 0. 0.25 is 2 to the power of what? I just said that a little bit earlier. -2. And 0.125 is 2 to the power of -3. Very good. Well, guess what? We have a binary number now. It just doesn't look like a binary number, but it is a binary number. Because what is a binary number? A binary number tells you the quantity, which is the digit, of each power of 2 in order to represent a particular value. We have the quantity, 0 or 1, of each power of 2 at this point. Is that making any sense? Okay, 64 is a decimal number. But because you know 64 is 2 to the power of 6, what do you think 64 looks like as a binary number? It's 1 followed by 6 zeros. Okay? The number of zeros after the 1 indicates the power of that number as a power of 2. So the first one becomes 1, 0, 0, 0, 0, 0, 0 in base 2. I have to use the 2 here to explicitly say this is not a million. This is 1 followed by 6 zeros in base 2. What about 2 to the power of 1? What does it look like as a binary number? 1, 0. Okay? What about 2 to the power of 0? Well, that's tricky. It's just 1, right? Because the number, whoops, base 1. It's just 1 because 2 to the power of 0 has 0 between the 1 and the decimal point. So that makes it just 1. What about the negative ones? 0.01 in base 2 is 2 to the power of -2. Because 0.1 in base 2 is 2 to the power of -1. So the number of places to the right-hand side of the decimal point tells you how negative the power is. If it is 1 place to the right-hand side of the decimal point, it is 2 to the power of -1. But it's the same way that we deal with it in base 10. 0.1 is what is 0.1 as a power of 10? Come on. 0.1 is 10 to the power of -1. What about 0.01? It's 10 to the power of -2. It's the same way here. Okay? All right. So now that we have this number kind of spelled out in this form, I just deleted something that I did not want to. Just this part here. Okay, so we have one more, which is 0.001 in base 2. That takes care of the eighth. Okay. What do you think the sum looks like? They're all base 2 numbers now. All right, so this is 1, 0, 0, 0, 0, 1, 1.011 in base 2. Are there any questions about how the base conversion worked? No? Yep, go ahead.
Sometimes I see fours.
Hmm?
Like if you were to group the digits in fours.
When you group the bits in 4, they become, it's an easy way to convert it into hexadecimal, into base 16. Yep. The reason why we like base 16 also is because binary numbers can be very long, lengthy, but base 16 can be a lot more compact. But the conversion between base 16 and base 2 is very easy. It's just groups of 4 and then groups of 4 and then groups of 4. But we're not going to get into hexadecimal just yet. I just want to get through with binary first. Yep, go ahead.
So when you did the final number, the 1000, 11 the 1 1 came. You replaced 0 in 10 with the 1.
Okay, let me do kind of more step by step this time. Paste it here.
Yes, that's where I stopped.
See how it all line up?
Yeah, so 0 was replaced with the 1. Okay. Thank you.
You're welcome. There you go. So that makes everything kind of line up a little bit better, and you can see how I end up with the final answer. Yep.
So 2 to the 6th power plus 2 to the 1st power plus that. What number is that representing?
This number in binary is the same thing. It represents the same value as 67.375 in decimal, in base 10. But I broke up the numbers. I broke up the values differently. Okay. Any questions? Yep. Go ahead.
So that's how the computer writes down, stores the information, like with the number
Well-
$67 and $3.75.
Well, inside the computer, it only has zeros and ones. Okay, so that means it cannot represent a number using base 10. There's no way a computer can represent a number in base 10 because it's all in bits, bits, binary digits. So we have to somehow boil numbers or the values that we want to represent into base 2 first. Okay, so that's why we break it down into base 2 or powers of 2, and then recombine all those digits into a bit pattern of this one here. So internal to the computer, yes, if you want to represent 67.375 in decimal, this would be the bit pattern to represent it. Now the decimal point is kind of the tricky part. Where is the decimal point in the bit pattern? That's kind of like a tricky point. We're not too concerned about that for the time being. Yep.
Doesn't decimal imply base 10?
Say again?
Does decimal imply base 10?
You mean the decimal point?
Yes.
Well, I suppose I would have to call it a binary point. So this is a binary point, and so is this, and so is this. Okay, because a decimal point implies it's decimal, right? And implies it's base 10. But the point is where the unit is.
Where it goes in positive thing.
Before it goes into fractions. Yep. All right. But it looks like another exercise is probably beneficial. Let's convert the same number to base 3. Okay? All right. So in base 3, what are we dealing with? If you want to represent a number in base 3, you have to think in powers of 3. 3 to the power of 0 is 1, 3 to the power of 1 is 3, 3 to the power of 2 is 9, 3 to the power of 4 is 3 is 27, and it's 81, and so on. Okay, so we want to convert this number into a base 3 number. So once again, we look at 67. 375 is not going to be a very nice thing to convert, so I can give you an approximation, but not exact. Okay, certain values cannot be represented exactly using a fixed number of digits. Just like 1/3 as a decimal number. What is 1/3 as a decimal number?
0.33.
It's 0.3, but the 3 is recurring, right? It never ends. So the same thing, in other bases. Sometimes, you encounter a particular value where it cannot be represented using a fixed number of digits. A part of it will be recurring. Same with this one here. Okay, but we'll start with the easy part. Okay, what is the number of the largest power of 3 that is less than or equal to 67? 3 powers of 3. 27. How many of 27s do we have? 2. Okay, very good. So this was 2 times 3 to the power of 3, because 27 is 3 to the power of 3. And what is the remaining portion after we subtract 54 from this number? 14 times 375. Okay. So we, sorry?
13.375. 13.37.
Oh, 13? Oh, you So we look at this portion here, and then we say, what is the largest power of 3 that is less than or equal to 13, and how many of those do we have? It has 1 9, okay? And 9 is 2 to the power of 3 to the power of 2. Okay, very good. So we have 1 of 3 to the power of 2. And once we take care of the 3, we have, what, 4.375 left? Okay. So now we take a look at this number, and then we say, okay, let's take care of the 4.375. What is the largest power of 3 that is less than or equal to 4.7? It has 1 3. Okay, very good. So it has 3. It has 1 of 3 to the power of 1, and then the remaining portion is going to be 1.375. Okay, all right. So now we look at 1.375, and then we ask, what is the largest power of 3 of this that is less than or equal to this number, and how many of those do we have? Yep, exactly, same thing. Okay, we have 1 of 3 to the power of 0. Okay, very good. So we'll just write it down. 1 of 3 to the power of 0, and then the remaining portion is now 0.375 in base 10. All right, so we'll take a look at this, and then we ask, we look at this portion here, and then we ask, what is the largest power of 3 that is less than or equal to 0.375 in base 10? So go ahead. It's 1 of 3 to the power of negative 1. Right? Okay, so we'll take care of that. So we have 1 of 3 to the power of negative 1. That takes care of 0.33333 and so on. So we have how much left? We have 0.042333, right? Okay. I can write programs, but I can't do math. 0.375 minus 0.333 is 1.7. Can't do math. All right. Let's double check. Trust myself here. 0.375 minus 1 divided by 3. Yep. Okay, that's correct. Okay, so we can keep going. By the way, this one is not going to end. Okay, so if you look at this number, what is the largest power of 3 that is less than or equal to this number, and how many of those do we have? I think we are talking about. Okay, so let's look at what is 1/10 first. 1/9, sorry. 1/9 is this. We don't have any ninths, so the next one is 27. Okay, that works okay, so we'll take care of that first. So it does have 1 of 3 to the power of negative 3, and then plus the remaining portion. So we have 0.0417 minus 1 divided by 27, and we have this amount left. And you can see how this process can continue. Basically, with each step, I'm just asking the same question over and over again. What is the largest power of 3 that is less than or equal to this value? And how many of those do we have? Once we figure out, we take care of that part, we subtract it from that remaining portion, and then keep going until it is either 0 or we run out of digits. One or the other. And that's conversion into base 3. So if I ask you to convert into base 7, would you know how to do it? It's tedious, it's really troublesome, especially for the fractional part. But do you know how to do it? The how part is more important than how quickly you can do it. Okay, that's base conversion. Now remember, I said a little bit earlier, if you know how to make change, for a certain dollar amount, it is more complicated than this. Why do you think I said that? Let's take a look at the denomination of the money system that we use. Okay, let's start with a penny, and we'll only use the more common type of denomination. This is a penny. What is the next one? Nickel. Nickel is 0.05. And the next one is a dime. And the next one is a quarter. And the next one, a dollar. Yes, I know there are half dollars, but they're not common. Okay, so we have a dollar, and the next one is, yep, 10, 20, 50. I don't have anything beyond 50, so I have no idea what is common after that. I've never touched anything beyond 50. So, okay, just look at these numbers here. Do you see a repeating pattern anywhere? Let's take a look.
Base 5, right?
Nope, not base 5. From 0.01 to 0.05, the multiplier is 5. From 0.05 to 0.10, the multiplier is 2. From 0.10 to 0.25, the multiplier is 2.5. From 0.25 to 1, the multiplier is 4. And then we go back to 5. And then we have 2, 2, and then another 2.5. I do not see any regularity at all. And yet you can do it. You can do it without writing it out, without doing all the steps that we have done so far. What is that telling you? It's telling you that you have more you're more capable than you know. You just have to think in a different way. Base conversion is easier than this because guess what? The multiplier from one denomination to the next one is a constant. It is always doubling in base 2. It's always tripling in base 3. Okay, so if you think in that direction, in that particular way, then you can convince yourself that you know base conversion already. You just have to think in a way that connects to what you already know. Just tweak a little bit of part of it and say, oh, okay, instead of going from $1 to $5, it's 1 to 2, 2 to 4, 4 to 8, 8 to 16, and so on. And then in the opposite end, it's going from 1 to a half to a quarter to an eighth, and so on. Then you already know how to do it. You just have to rethink it a little bit, readjust, and you're done. Are we still doing okay so far with the lecture at this point? Is everyone kind of comfortable with the concept of base conversion and what a base really is?
I can't see it off the top of my head, but could you write out the 67.375 in base 3? I know it's 2 times 3 to the third plus 1 times 3 to the second.
Okay, sure. I can write down the approximation. I'll stop here, okay? So here I'm going to say approximately equal to. Okay, so what you want to do is to say this is 2 followed by 3 zeros in base 3. The next part, okay, I'm going to align things a little bit so it's easier to see. This one is 1 followed by 2 zeros in base 3. This is 1 followed by 1 zero in base 3. And this is just 1, okay, in base 3, whatever base, doesn't matter. This one is 0.1 in base 3, and then this one is 0.001 in base 3. Is that okay so far? Now how can I do this conversion? The power of 3 on the positive side tells you the number of zeros that you have to pad on the right hand side. It's just like 1,000 in base 10 is 10 to the power of 3. But how do we write 1,000 as a base 10 number? 1 followed by 3 zeros. So the power of the base is telling you how many zeros that you need to write on the right-hand side of the digit. On the fractional side, the power tells you where the digit is to the right hand side of the decimal point, or in this case, decimal binary, what is base 3? 4 is quad, 3 is tri, so this would be a trisimal, right? Trisimal point, okay? And this one is to the power of -3, so it is 3 places from the point it's here, point here. But once we convert here, the rest is easy, because now we can just say the rest is just the alignment of things, right? You just have to align everything correctly, like that, and then the point has to go here. And once everything aligns, correctly, then you can say this is 2, 2, 1, 1, 1, 0.101. It's going to be a repeating pattern. I didn't finish the entire process, but approximation, wise, is about that as a base 3 number. Okay. Any questions? Yep.
So the computer sees the 211 point over, and then it knows that it's 67.375?
No, the computer does not know that. You have to do the base conversion. Internal to the computer, everything is base 2. They're all zeros and ones. But if you want a computer to output something, then you have to specify which base you want the number to be how you want the value to be represented. If you're inputting something, like if you're typing something into the computer, you also have to specify what is the base of the representation. But internal to the computer, it is all zeros and ones because the transistor is either on or off inside the computer. Right. Any other questions about base conversion? No questions about base conversion. All right. If there are no questions about base conversion, well, I have just a few more examples here, but they're nothing more than what we have already talked about. Okay. Okay. So now the question is, how do we represent an integer or integer values inside the computer? There are different ways to do it. Okay. I'm using BCD or binary coded decimal here as an example. We're not going to use BCD in this class. Okay. In C++ programming class, we're not going to use BCD. But BCD was used a lot on mainframe computers, especially computers that has to crunch numbers related to money, okay, like Social Security, your banks, any type of financial institution. They will still be using BCD at some point because it can represent values exactly where binary representation cannot. So with modern microprocessors like the Intel processor or the ARM processor and so on and so forth, we typically want to use a base 2 number. Okay, because it's bit, we just have to specify the number of bits per number, and that is called the width of integers. Okay, a typical width is 32, which means internal to the computer, an integer is represented by a 32-bit pattern. You have 32 zeros and ones to represent a value. Am I making sense? Okay, so far. Okay. So. The other thing is the compiler, the C and C++ standard as a programming language, does not indicate the width of the type called int, which is an integer type. Okay, and it is for the most part dependent on the platform that you're running the compiler on, or it depends on what the compiler is compiling code for. If you're compiling code for a 32-bit processor, an int is probably 32-bit wide. Not always, but most of the time it is. If you're compiling for a 64-bit platform, it is usually a 64-bit wide integer. If you're compiling for a 16-bit platform, an int is usually 16-bit wide. So it depends on a lot on the target platform of your compiler. Okay, which processor is the code supposed to run on, and that will kind of determine the width of the integer. The value that you can represent using an integer of a certain width is in this range here. W is the width, and this is the smallest or most negative number you can represent using W as the width of the integer. And this, on the other hand, is the largest or most positive integer you can represent using W as the width. Okay, let's think about actual numbers here. 32-bit. Okay, 32-bit is fairly common, at least in the past. Now it's moving on to 64-bit. But with 32 as the width, what is the most negative value you can represent? Just approximately. I know you guys don't want to deal with exact numbers, but approximately how negative can the value go with a 32-bit number? Well, let's think about it. I'm just going to write this using the whiteboard. This is a trick that you can also use for many other things, for estimating stuff. Okay, so we're dealing with 2, negative 2 to the power of 32 minus 1. That's the most negative value that you can represent using a 32-bit number. Is that part okay? I'm just basically making W 32 bits. Is that okay? All right. So I want to estimate how negative this number is. So the first thing is to take care of 32 minus 1, which is 31. That's the easy part. So what approximately is 2 to the power of negative 2 to the power of 31? And this is how it's grouped. Okay, the negative is on the outside. I'm not taking a power of negative 2. I'm taking the negation of 2 to the power of something. All right. So what you want to do is to remember one thing. 1,000 is a base 10 number. It's approximately 1024. But 1024 is special because it is exactly 2 to the power of 10. Okay, so this is how we do the approximation. We are looking at one base 10 number, a power of 10, and saying, oh, it's about the same as this power of 2. That becomes very handy. Because now we can look at this number here, and we say, we can rewrite this number here. The negatives are on the outside, so we don't really care much about it. So this is 2 to the power of 10 times 2 to the power of 10 times 2 to the power of 10 times 2. Is that making any sense to you? Because we have a 31 here. 31 is 10 plus 10 plus 10 plus 1. This 1 is implied, but you can stick 1 here too. Doesn't matter. Is that okay so far? So now I can say the approximation. Because now I can say, oh, this is approximately 1,000. This is approximately 1,000. This is approximately 1,000. That's just 2. So what is this quantity? It's 10 to the power of 9, which is also known as a billion. So this is about negative 2 billion. Is the most negative quantity that you can represent using 32 bits. Is that enough for our national deficit? Is it close? That's okay. We can move on to 64-bit numbers. That will take care of us for a few years. Yep.
Why would we use 1,000 and not 1024?
Because I want an approximation. Because we still think in base 10 for the most part. So I just want to give you a sense of how negative. What is the magnitude of this negative number? Right. Any other questions related to stuff that we have talked about so far? Questions? Okay. Row sheet. Thank you. I keep forgetting the row sheet. Right. So now that we understand how numbers are represented in the computer as integers, and they're all basically integers of either 16, 32, or 64-bit wide, what about those other numbers like 24, 27, 31, 37? Well, they're just very uncommon. Okay, with modern microprocessors, the width of an integer is usually a power of 2 itself. So you can see that 16 is a power of 2, 32 is a power of 2, 64 is also a power of 2. In the past, they did have mainframes with really kind of odd number of bits per integer. but we don't have those mainframes anymore. All right, so back to bitwise operations. So with bitwise operations and versus logical operations, we'll deal with logical operators first because those are things that we already understand. So this is how I define the truth table of logical AND, otherwise known as conjunction. If I have one column representing a variable x and one column representing a variable y and one column to represent the expression of x logical and y, then we have this truth table. The first two columns, the leftmost two columns, represent input into the expression. The third column represents the output of the expression, the value of the expression, or basically the output. So what you see here is 0, which is false, and 0, which is false, is false. False and non-zero is true, so false and true is true. True and false is false. And then finally we have true and true is true. Is that consistent with your understanding from the previous class in CISP 300, 301, or 370? Except in this class, we don't say true or false. We say 0, which is false, and non-zero, which is true. Is that part okay? Okay.
Why not 1? Well, instead of saying not 0, why just say 1?
Because that's what the programming language standard specifies. Anything that is non-zero is treated as true. All right. So that's basically this part answers your question. Okay, because non-zero can be anything other than 0. Can be a 5, can be a -2, can be 10, can be -3001, and so on. All right, so this is the other logical operator that you should be familiar already at this point. It's logical OR, otherwise known as disjunction. And with disjunction, it's kind of like the flip side of conjunction. The only time a disjunction or the OR has a 0 or false is when both inputs are false. If you have at least one side of a disjunction being true, then the entire thing is going to be true. Are there any questions about this particular truth table? Yep.
Could you elaborate on why in the disjunction the non-zero takes precedence over the 0?
Say again?
In the disjunction table,
Yeah.
the non-zeros take precedence for the output.
That's because that's how disjunction is defined. Because non-zero is true. Okay, when you look at true, false, and disjunction, false or false is false. True or false is true. True or false or true is true. True or true is true. So that's why the other 3 rows, they all have true as a result. So are there any questions about these two tables? One to define conjunction, one to define disjunction. They are basically the same thing that you already learned from the previous class, except in this class we don't say true or false, we say non-zero and 0. That's the only difference. And also the symbols are also kind of more awkward. Instead of spelling out AND and OR, we are now using C++ operators. The conjunction is 2 ampersand right next to each other. And disjunction is 2 vertical bars right next to each other. Okay? Any questions about the symbols of disjunction and conjunction? What about negation? Logical not is negation. Well, not false is true, and not true is false. That's how negation is defined. And negation is a single exclamation point. That's the symbol for negation, logical negation. Are there any questions about the logical operators before we move on to bitwise operators? No? Okay. All right. Before we move on, we'll still go ahead, just give you one example here. And I'm going to hide the answer just in case, you guys, I think some people read that part already. So what is the result in C++ of 5 logical AND in parentheses 3 is less than 4? How would you describe the output of this expression?
True.
Okay, but remember there's no such thing as true in C++.
Non-zero.
Non-zero, exactly. All we can say is it gives you a non-zero value. But which non-zero value? We have 4 billion non-zero values. 4 billion, not 2 billion. Well, because we have positive and negative numbers, right? The C++ standard does not say. It just says it can be any one of the 4 billion something non-zero values. So don't count on it being 1. Don't count on it being -1. Don't count on it being 10 or whatever. It can be anything. Right. So now we move on to bitwise operators. Now bitwise operators are a little bit funky because the operation is applied to each bit of an integer. So when we look at a truth table, it is no longer looking at the entire thing, it is looking at each individual bit. So if you are dealing with a 4-bit number, if you represent a 4-bit number as A, B, C, D, then we're going to separate the 4 individual bits, and each one is going to be processed, using the bitwise operator. Okay. I'll give you some examples later on too. So when we look at a truth table defining your bitwise operation, it looks almost identical to the to the logical AND, except in this case, what are the differences here? Well, I can point out the differences. First one is instead of logical, it's now called bitwise. Okay, no big deal. And I don't call this conjunction anymore. Okay, I just call this bitwise AND. It's not conjunction. But when you look at the columns, they're also labeled differently. Instead of saying X, I'm saying this is bit I of X. Because X is a multi-bit integer. And I'm only looking at one digit, one binary digit of the entire integer. So I focus on one bit at a time. But when you look at the rest of the table, the other thing that is different is instead of double ampersand, it is now single. That's a very common mistake, is to use a single ampersand when 2 are needed. Okay? Now the other way around is less common. If you intend to use a single ampersand and accidentally put in double ampersand, that is not a very common mistake. But the most common one is when you need 2, you put in 1, the compiler doesn't complain because it is still valid syntax, but the operation becomes different. Okay? It doesn't do what you think it should do anymore. Bitwise OR is about the same. So we'll focus on these two for the time being, and I'll work out one example just so that you know how it works. Okay? All right, so let's take a look at bitwise AND, and I'll just pick 2 numbers kind of randomly. 56, bitwise AND, let's say 14 here. No, 14 is not too much fun. Let's pick 12. 12 is a little bit more fun. Okay. You look at this expression, unless you plug it into the computer and figure out the answer, how do you do this by hand? Go ahead.
Just a quick question. So when actually programming and making a statement X and Y, should I plug in the 2 AND signs or just one?
It depends on whether it is a logical operation or it's a bitwise operation. If it's logical, you need double. If it is bitwise, you need a single.
Okay.
Okay, so let's take a look at this one. The first thing you have to do is to convert 56, which is a base 10 number, into its base 2 representation. And then you have to look at 12 and convert it into its base 2 representation. Because the operation of a bitwise AND is applied to each individual bit of a binary number. So you can't really work out what it is going to do unless you know the base 2 representation. So I'm doing the base conversion right now. 56 is, let's see, it's divided by 16 is 3, okay, 0, 0, 1, 1, with a remainder of 8, which is 1, 0, 0, 0. This is also the same as 7 times 8, which is correct. Okay. Now, how can I come up with these calculations so quickly? Now, the fact that you know it's 7 times 8 is really handy, okay? What do you think is 7 in base 2? How do you break 7 down into just powers of 2? It's 4 plus 2 plus 1, okay? Now, 4 is 2 to the power of 2, 2 is 2 to the power of 1, 1 is 2 to the power of 0. So as a base 2 number, the value 7 is 111 in base 2. What do you think is 8 in base 2? 8 is 2 to the power of 3. So in base 2, it is 1 followed by 3 zeros. Okay? When you multiply 111, which is 7, by 1000, which is 8, what do you get? 111 followed by 3 zeros. Okay? So that part works the same way in base 2 as it is in base 10. What about 12 in base 10? What do you think is the representation of 12 in base 2? It's 1100 because it is 3 times 4. 3 is 11, 4 is 100. So 3 times 4 is 11 followed by 2 zeros. In time, you will be able to do this too. I can throw out a number between 1 to, let's say, 255, and you can just kind of mentally go through the conversion process and come up with the bit pattern. Okay, so we look at these numbers here and say, okay, but what is the bitwise AND? The bitwise AND means you look at the number. This is the first number, and this is the second number, and then you apply the truth table to each individual column. You look at the column here, 0, 0. According to the table, what should be the bitwise AND of 0 and 0? 0 and 0 is 0. 0 and 0 is 0. What is 1 and 0? All right, 1 and 0. What is 1 and 1? 1. 0 and 1? 0 and 0, 0. 0 and 0 is 0. So that's the final bit pattern. What exactly is the value represented by 0, 0, 0, 0? Leading zeros are not really important. 1, 0, 0, 0 in base 2. It's just 8. Exactly. So now we have just calculated 56 and 12 is 8. Okay? The expression gives you a value of 8. Okay? What about 56 double ampersand 12? What would that give you? Double ampersand is logical AND.
Non-zero.
Any non-zero value, okay? Okay, so you say, well, but that seems okay because 8 is also a non-zero value, so it seems like these two operators is somewhat interchangeable. Well, let me give you another example where it is not interchangeable. Okay? I'll give you one easy one that is not interchangeable. 8 and 4, bitwise AND. Okay, so we'll spell out everything. 8 is 1000, 4 is 0100. And I want to do a bitwise AND of these two. What is the result here? 0, 0, 0, 0. So that means if you use bitwise AND, 8 and 4, 8 bitwise AND 4 is 0. But when you use logical AND, 8 bitwise logical AND 4 is non-zero. Here we go. So that's why you have to be very careful when you're dealing with the AND operation or the ampersand symbol, because whether you use double or single, it can change the behavior of your program, but in a very weird way. Sometimes it works, sometimes it doesn't work. Sometimes it works for a particular compiler and it doesn't work for another compiler, because the implementation of the compiler can also have something to do with this. Are there any questions about how to work out the result of a bitwise AND? Well, if you know how to work out bitwise AND, the other ones are fairly easy too. The other ones are just a different table. Bitwise OR is just like regular logical OR, except instead of non-zero, we specify ones, but it only applies to one bit of the entire pattern. Negation, same thing. Okay, a 0 turns into a 1 turns into a 0, but it is for each individual bit of the number. But in bitwise operation, they also have bitwise exclusive OR. Exclusive OR is almost the same thing as a regular OR, except one exclusive OR 1 is a 0. Okay. Are there any questions about this one? Okay. I'm pretty sure someone is asking, but where can I get some exercise to do all this stuff? Well, guess what? I got you some exercises. And it is in basic syntax. If you scroll down to here, there's base conversion and bitwise operation exercise. It's in the form of a quiz, except there's no time limit. There's no due date and no time limit, nor how many times you can try it. Your score is based on your highest score. So you can do this as many times as you want, and if you want to do it a few more times just for exercise purposes, feel free to do it. Yep.
Explain that 8 and 7.
The 8 times 7 thing? Sure. Okay, so I'm going to use the whiteboard for that purpose. You're asking about 56. 56 in base 10 is 8 times 7. Okay, we know that. 8 in binary is 1000 in base 2. And 7 is 111 in base 2. When you multiply numbers like these, it's the same thing as in base 10 or any other base. If one of these numbers is really just a 1 followed by a bunch of zeros, it means you just have to add zeros, the same number of zeros to the other one to get the product. So that's why the result of this is just 111, which comes from this part here. And this is only contributing zeros on the right-hand side. So you just pad all those zeros on the right-hand side, and that becomes the result. And then to make it a 8-bit number, you have to pad one more zero here, but that's just leading zeros, which doesn't change the value of the representation. Sure. There's another way to do it too. I actually mentally I did it by base 16 conversion first, and then I converted back into binary. But this is the other way to do it. Base 16. What is base 16? Okay. In base 16, each digit has 16 choices, right? Because in base 10, each digit has 10 choices, 0 to 9. In base 2, each digit has 2 choices, 0 and 1. In base 16, each digit has 16 choices. But we only have 10 digits, 0 to 9, so how can we have 16 choices? Well, we borrow the letters, okay? We borrow A to F from the alphabet to become 10, 11, all the way up to 15 for one single digit, okay? And the way you convert between base 16 and base 2 is just a table lookup. You group bits by 4 chunks, and then you look at the 4-bit chunk, and then each 4-bit chunk is corresponding to one base 16 digit, and that's the easy way to do the conversion. In this class, at this point we're not too concerned about base 16, but eventually I will probably teach you guys how to do with base 16 numbers, because they are also very useful in computer science. All right. So are there any questions about the stuff that we have talked about today? Yep.
I have a quick question. We have the digits, the answers. What if one of them is longer and then one shorter? How do you align them up?
It's the same way you do with base 10 numbers. Okay, so let's deal with some base 10 numbers. So let's say we want to add 4016 and 301. Okay. This is longer. This is shorter. How do you align these? You align it by the implicit point. There's implicit point here. There's an implicit point here. That is your alignment. Same thing with binary numbers.
But I'm talking about the table, you know, when you're trying to figure out whether it's 0 or 1.
The table.
Bitwise table.
Oh, the bitwise table.
Yeah.
Okay. That one works the same way as the other table. Let me go back to the table first. It works the same way as the other table, where this specifies, bit I of the first number is a 0. This specifies, bit I of the second number is a 0. And this specifies the output of the bitwise AND. So these two columns are the inputs, and this column is the output. And then each row represents, one particular case, one particular input pattern, and then its output. So if you pick one row, let's pick this row here. It means, if bit I of one particular bit of X is a 1, and then the same bit of the second number is a 0, then this particular bit of the output is a 0.
And you start from right to left.
The first two columns are the inputs. The third column is the output.
If you go back to your notepad, I can show you what I'm talking about. Okay, so see how the answer there, all of them align?
Yeah.
They have the same length.
Yeah.
What if one of the answers, when you convert it to base 2, is shorter and one is longer?
Then you pad zeros to the left-hand side of the short one.
Okay.
Yes. Because padding zeros to the left-hand side of the short one does not change the value, but it just makes the zeros explicit, so you can perform. Now I understand your question. Sorry, I didn't quite understand it. Yep. All right. All right. So this is the end of today's lecture. The quiz or your exercise is active already, and remember, you can do it as many times as you want. Okay, there are multiple test cases. I know you guys don't want to do the same thing over and over again, but the calculation questions will change. There are 50 cases, so if you want to practice and just say, okay, now you can work out this bit pattern. Give me another one. You can just do it again. It will give you a different question. Okay, if you come in late, you have to sign the row sheet. It does count for your grade, but that's good because most people would just do it enough times to get an A and do A. There's no due date, there's no no restrictions.
I just saw that in the row sheet. I didn't sign last time.
The other time, I remember you were here, so
Yeah,
you can go ahead and sign it
I
back.
did sign it, just that don't want to be marked over there.
Oh, okay.
Thank you.
Could you check the file that I uploaded? I just want to make sure that you.
Oh, okay.
So you did it with the program export format.
Okay, let me stop.